Hello again, and welcome to our lecture on parametric equations. I think you'll find this really a neat lecture. There's some very interesting examples and some pretty pictures to look at. So let's step back and remember that we talked about functions a while ago, and we always said that the notation was like y equals f of x. And we thought of x as being an independent variable in the domain. You feed it in, and the rule says y is f of x. So it's a function of x. Well, we're going to take it up a little bit, take it up a notch, and now have x and y be functions of a third variable. So we're going to have, in a sense, two functions going around, but x and y will still be plotted in the xy plane. So in particular, x and y will be functions of, say, the variable t, or it might be theta or some other letter. And so every time you input a t value, that generates an x value and it generates a y value, and then you could plot that xy pair in the coordinate system. So it's kind of a neat way to generate pairs of points, both being functions of that third variable t. And something that'll be interesting in this lecture, we'll be using our knowledge of trigonometry and of conic sections quite a bit to describe some very interesting curves. And in particular, we'll talk about motion. Parametric equations are very good in describing motions of particles. The main reason being t could be time, and x and y could be the position of a particle as a function of time. So to get started, let's, as I usually do, look at a fairly simple example to understand how this independent variable t really works. So I'm going to give a function of x and y, both being functions of t. So x will be t squared minus 4, and y will be t over 2. And let's restrict the domain. Let's say t is between minus 2 and 3. It's inside that closed interval. So what does the picture look like as t varies from minus 2 to 3? T takes on all these values, and each time you take a value, it generates an x and a y, and then you plot xy. Well, I suggest you form a table of values. And here's how this might work. Along the top, you might have selected t values. You could think of t as time. And they would start at minus 2, and then you would pick other points, say minus 1, 0, 1, 2, and stop at 3. And for each of these values, you generate an x and a y. For example, if t is minus 2, what's x and what's y? Well, you would plug minus 2 in for the formula for x, and you would get minus 2 squared, which is 4 minus 4. So x would be 0, and y would be minus 1. Minus 2 over 2 is minus 1. And then you would plug in other values. For instance, if I plug in 0, what do I get? X will be 0 squared minus 4, or minus 4, and y will be 0. So I'll plot the point minus 4, 0, corresponding to t equals 0. And then I'll finish off with t equals 3. What do I get? X will be 3 squared minus 4. 9 minus 4 is 5. And y will be 3 halves, and that'll be the y coordinate of the point. So you fill out this table of values, plot those points, and then connect them with a smooth curve. And here's what you get. Isn't this an interesting picture? I really like this picture. It starts down there with t equals minus 2, and that corresponds in Cartesian coordinates, the point 0 minus 1. And then it kind of bends and goes out when t is 0. It seems to be the furthest to the left. And that point, of course, is minus 4, 0. And then it comes back, and finally at t equals 3, it's kind of finished off there at the point 5, 3 halves. Okay, so an interesting picture. Let me ask you some questions about this picture. Suppose you were just given this picture way back in lecture 1. And I asked you, is this the graph of a function? Is this the graph of a function? And of course you would say, no, it doesn't pass the vertical line test. This is not the graph of a function. So already we see an advantage of parametric equations, don't we? They're pretty good at graphing things that might not be even functions. Let me ask you another question, a little bit deeper. What do you think this curve looks like? What do you think this curve is? Is it a straight line? Duh, no. Is it an ellipse? Don't think so. What do you think it is? Well, it turns out it's a piece of a parabola. And let me show you how you get it in this case. This is called eliminating the parameter. And you can do this sometimes with parametric equations. Not always, but sometimes you can get rid of that variable t and obtain an equation involving just x and y. And then you'll see, oh, I know what that is because I see the equation in our friendly xy coordinates. It's not at all obvious when you have parametric equations what the graph's going to look like. You may have to point plot it or use your calculator to show a picture. But once you get it into xy land, you eliminate that variable t, you're often more confident in the shape of the graph. So let's eliminate the parameter in this case. Here's how you could do it. Notice the equation for y is t over 2, so that means that the variable t equals 2y. And take that value and plug it into the equation for x. And you'll get x equals, instead of t squared, you get 2y squared minus 4. In other words, x is 4y squared minus 4. And I look at that and I go, oh, I know what that is. That's a parabola. And in fact, using our knowledge of conic sections, we could, discover where the focus is, etc. But that's not necessary here. Let's be confident that we know that's a parabola, and it does look like the picture there. Now, of course, it's a piece of the parabola, isn't it? It's not the entire parabola. Okay, let me point some things out. This parabola is not a function, right? It didn't pass the vertical line test. So again, one of the powers of these parametric equations is they can graph curves that are not the graphs of functions. It's also not always possible to eliminate the parameter. You might have a very complicated set of parametric equations and you just can't get rid of the parameter t. We were lucky here. It was fairly simple. But there's something deeper that I want to point out. In that picture of the parabola, we had a certain orientation associated with it. As t got larger and larger, we went around the parabola. It started at one point, and as t grew, we went a certain direction. That orientation of the curve is completely lost when we eliminated the parabola. When we got the equation x equals 4y squared minus 4, that's just an equation of a parabola, but I can't tell which way we're going on the parabola. So a great advantage of these parametric equations is they have a built-in orientation. You know which way you're going. As the parameter increases, that's your direction. All right, let's do another example. These are kind of fun, I think. Let's look at the curve and we'll use some trigonometry now. X is 3 cosine theta, y is 4 sine theta. I've changed the parameter on you. Instead of using t, I'm using theta, because I'm kind of imagining this as theta being an angle, but you don't have to say that to yourself. Just for every value of theta, and I'll make it on the interval 0 to pi, for every theta value, you generate x equal to 3 cosine theta, and you generate y equal to 4 sine theta. What's this going to look like? If I were to graph this, what's it going to be? You'll be surprised. This is really cool. All right. What could we do? Well, one way to do it, of course, is use a graphing utility. You plug it in. Graphing utilities have parametric modes. It's really interesting. I'll come back to that in a minute. So you could, in a sense, cheat and graph it on your calculator. But we're going to do some mathematics here. We're going to take these equations and eliminate the parameter, and then suddenly you'll see what it looks like. All right, so our equations are 3 cosine theta is x, 4 sine theta is y. Can we get rid of the parameter? Watch this neat trick. Solve for cosine theta, and that would be x over 3, and sine theta would be y over 4. Okay, now why did I do that? Remember the fundamental identity from trigonometry? Cosine squared plus sine squared is 1. Well, I have an expression for cosine and an expression for sine. Let me add up their squares. What do I get? Instead of cosine squared, I get x over 3 quantity squared. Instead of sine squared, I get y over 4 quantity squared. Add them up. It equals 1 by the trig identity. And now simplify it. X squared over 9 plus y squared over 16 equals 1. Do you recognize that guy? Right. That's an ellipse. Isn't this neat? Those parametric equations trace out an ellipse. Here's a picture of it. Here's a picture of that ellipse. Let's savor it for a moment. I'm going to plug in some values on that ellipse. For example, when theta is 0, where are we on the ellipse? Well, when theta is 0, x is 3 cosine 0, or 3, and y is 4 sine 0, or 0. So when theta is 0, we're at the point 3, 0 down there on the x-axis. How about when theta is pi over 2? Well, cosine pi over 2 is 0, sine of pi over 2 is 1, so we're at the point 0, 4. We're up at the top of the ellipse now. And in fact, you can see that the orientation of this parametric curve is counterclockwise, isn't it? Isn't that neat? When we wrote down the equation of the ellipse in Cartesian coordinates, xy coordinates, we lost that orientation, didn't we? All right, let's do another example. Let's describe lines using parametric equations. And this, again, will be kind of neat, I think. I think you'll like it. All right, so let's imagine we have 2 points in the plane, x1, y1, and x2, y2. I'm using subscripts here to distinguish the 2 points. I want to find the line joining them, and I'm going to use a parametric representation of that line. Well, let me show you the formulas, and then I'll verify to you that I got them right. So let x be the following parametric equation of the variable t. It's equal to x1 plus t times the quantity x2 minus x1, and y is y1 plus t times the quantity y2 minus y1. Now don't panic here. I'm going to plug in some values into those parametric equations and you'll see how they work. All right, watch how we do it. For every t value, and you know x1, y1, x2, y2 because those are given numbers, for every t value, out comes an x, out comes a y. And then you plot that point. For instance, when t is 0, what do you get according to these equations? Well, when t is 0, it simplifies to x equals x1 and y equals y1. So when t is 0, I'm at the first point, x1, y1. Now let t equal 1. Well, when you plug in 1 for the x part, you get x equals x1 plus x2 minus x1. The x1s cancel, and you're left with x2. And in the same way, you're left with y2. So when t is 1, I'm at the other point, x2, y2. So here's a picture of this line defined parametrically between x1, y1 and x2, y2. And notice there's a built-in orientation. When t is 0, I'm at the point x1, y1. And when t is 1, I'm at x2, y2. Where do you think I am when t is, say, 7? Yeah, I'm further down the line. And when t is a negative number, I'm up the other side. So as t varies from minus infinity to plus infinity, you go up and down this line. Isn't that neat? Let's do a quick example to show you how this works. Here are a couple of points, say 1, 4, and 6 minus 3. Those are 2 points in the plane. I'm now going to describe the line joining them using parametric equations. Of course, you could find the line y equals mx plus b, couldn't you? Find the slope and the y-intercept and all that. But we're now, going a little bit deeper into mathematics and doing parametric equations. So how would it work? The equations, remember, are x1 plus t times x2 minus x1 and a similar equation for y. We know all the characters, don't we? x1 will be 1. And then x2 minus x1 will be 6 minus 1. So the first equation is x equals 1 plus t times the quantity 6 minus 1. That's 1 plus 5t. How about that second equation for y? Well, now the y coordinates are 4 is y1 and minus 3 is y2, so it's 4 plus t times minus 3 minus 4. And you get 4 minus 7t. Let's check ourselves. Let's check ourselves here. What if t is 0 in these equations? Where am I? Oh, if t is 0, I'm at the point 1, 4, the first point. What if t is 1? Where am I? Well, the first equation gives 6, and the second equation gives minus 3. Bingo, I'm at the second point. Here's a picture of that situation. At time 0, we're at 1, 4, and at time 1, we're at 6 minus 3, and you see that as t varies, we go up and down this line. Now you might say, well, why did we bother describing a line parametrically when we could do it with y equals mx plus b, the slope-intercept form? Well, here's one reason. When you go on and take calculus, you'll be dealing with three-dimensional mathematics. And imagine a line in 3 space, a line moving through this room, a straight line moving through this room, say. Well, it doesn't really have a slope or a y-intercept anymore, does it? Those concepts don't mean anything anymore when you're in 3 space. But you can describe it parametrically, and that's how they do it in mathematics. So this idea of a parametric representation of a line is really important when you go to higher dimensions. All right, now, I hope you've enjoyed these parametric equations so far. You can develop equations for parabolas, ellipses, well, we saw an ellipse, hyperbolas, etc. One thing to keep in mind, the equations, the parametric equations for a curve are never unique. You can always change that parameter. Instead of using the parameter theta, you could use the parameter 2 theta, and then you would have a different parametric representation. And one thing to always keep in mind in this parametric lecture, that there's an orientation associated with a parametric representation. There's an orientation as t increases. Let me show you a fun example now. Do you have a bicycle? If you put a light on your wheel of your bicycle, say on the back wheel, and you're biking along, I'll try to bike along here, the wheel turns, but you're also moving forward. So that light, suppose it's nighttime, so you can only see the light on the wheel of your bicycle. And the light would go like this. It would kind of go around and then it would hit the ground, but you're going forward, so the light would keep going. It generates kind of an interesting looking figure, and it's called a cycloid. A strange word, a cycloid. And this cycloid, this moving light on your bicycle, has an equation. Let me show it what the equation is. It's x equal theta minus sine theta. Here I'm using the parameter theta. I could have used the parameter t or w or anything I wanted. And y is 1 minus cosine theta. So for each value of theta, you get an x and a y, and then you plot them. Well, I invite you to do this on your calculator. Plug in these two equations in parametric mode, and you'll have to find that on your calculator, and you'll get a picture like this. Isn't that a neat looking picture? The curve kind of goes along, and then it has a sharp corner, and then it starts up again, and then it has a sharp corner and starts up again. This cycloid always occurs in calculus courses. They like to study it because it's a smooth curve. It has no sharp corners except where it hits the ground there, where it hits the x-axis. And then it has a real sharp corner there. And that's always of interest to mathematicians. So try graphing this on your calculator. You'll have to do the following when you graph it. You'll have to set the domain for t, because t is now the independent variable. And in my picture, I've let t be between 0 and 25. Then you'll have to set the window, and the x dimensions I set to be between 0 and 20, and the y dimensions between -1 and 3. So there's a lot more to set there. And then you have to feed in the two equations in parametric mode. And most calculators use the variable t as the independent variable. And if you do that, you should get a picture that looks very much like this. If you struggle with it, read the manual. I always tell my students to do that. Read the manual. You know, if a student comes up and says, Professor Edwards, I don't know how to use my calculator, I have always two solutions for the student. One is read the manual, and of course they never do that. I always read manuals. I read the manual for my DVD player, and of course never understood it, and I never understood the calculator manual. The better way to understand it, what I tell students, and what I do, is say, talk to a different student. Because young people seem to pick up on these calculators so much better than I do. I learn a whole lot from my students as to how graphing calculators work, how to graph things like parametric equations. So again, if you struggle with this, try to read the manual or, talk to somebody who's had more experience with graphing calculators. All right, let's do an application. Projectile motion. If you take a physics course, you'll learn about how particles can move in space. And here's sort of the setup that we'll talk about. Suppose you have a projectile and it's launched at a height h above the ground, and it's at an angle of theta with the horizontal. So there's a certain angle of inclination here, an angle of theta with the horizontal, and it has a certain initial velocity, which we'll call v sub 0. You can imagine shooting an arrow. So the arrow, I'm shooting it above a certain distance h above ground at a certain angle, and I've got a certain initial velocity of that arrow, and out it goes. Well, from physics, you can derive equations for the path of this object, of this projectile, as parametric equations, as a function of time. And here they are. The x-coordinate of our object will be v0 times cosine theta, all times t. T is time. And y will be h plus v0 sine theta times t minus 16t squared. That 16t squared comes from the effect of gravity. As the projectile goes up, it gets pulled back to Earth. And the h, of course, is the distance above the ground that we fire this thing. All right. How about a particular example of these formulas? And we'll use my favorite sport, baseball. So here's the setup. You're in a ballpark, and the center field fence is 10 feet high. Okay, imagine a 10-foot center field fence, and it's 400 feet from home plate. So there's center field, way out there, a 10-foot fence. And somebody's hitting a baseball, and they're hitting it 3 feet above the ground. So they're making contact 3 feet above the ground, and at an angle of 20 degrees. So they're hitting it with their bat at a 20-degree angle above the horizontal. And suppose the speed, the initial speed of this baseball coming off the bat is 100 miles an hour. I know some pitchers can throw the ball 100 miles an hour, so let's assume that it comes off the bat at 100 miles an hour. And that turns out to be, if you change units, 146.67 feet per second. So I'm using units here of feet and seconds, not miles per hour. So here's the question. You've swung this bat at that angle with that initial speed. Is it a home run? It goes out to center field 400 feet away. Does it get over the fence or not? That 10-foot fence. Well, let's use our formulas to find out. Here, make a bet. What do you think? Think it's going to go over the fence? Well, let's find out. The equations were x is v0 cosine theta times t, and y is h plus v0 sine theta t minus 16t squared. Plug in the numbers. We get for v0 146.67 cosine of 20 degrees. That was the angle, 20 degrees times t. And y is 3. Remember, we hit it 3 feet above the ground, plus 146.67 sine 20 degrees times t minus 16t squared. calculate those cosines and sines on your calculator, x is approximately 137.82 t, and y is approximately 3 plus 50.16 t minus 16 t squared. Wow, kind of complicated, but we're doing a real physics problem here. Does it go over the fence? Well, let's find out how long it takes to get out there, 400 feet, and then when we get it out to 400 feet, let's see how high it is. So when x is 400, the baseball has reached the fence. So let's let x be 400 in that first parametric equation. And if x is 400, solving for t, you get 400 divided by 137.82. That comes out to be about 2.9. In other words, in about 2.9 seconds, the baseball has arrived at the fence. Question, how high is it? Well, plug that t value into y. You get 3 plus 50.16 times the time, 2.9, minus 16 times the time squared. Plug that into your calculator. It's a home run. It's about 13.9 feet. It clears the fence by 3.9 feet. Isn't that cool? Nice problem. You be the teacher for a moment. I really like these you be the teacher problems. I get a lot of them in the classroom. So here's a typical problem that I might get as a teacher. Student comes up to you and says, Professor, is the following set of parametric equations the same as this other set of parametric equations? The first set is x equals t and y equals t. So that describes a certain curve. And the other set is x equals t squared and y equals t squared. And that also describes a certain curve. Do these describe the same curve? Well, what do you think? Look at the first one, x equals t and y equals t. If you eliminate the parameter there, you get x equals y, don't you? Hey, that's a straight line, y equals x. I know that line. Well, eliminate the parameter in the second one. What do you get? You eliminate the t squared, you get x equals y. That's a straight line. That's the same straight line as the first one. So the student might say, I think it's the same line. But what do you say as the teacher? Well, they aren't quite the same. When we eliminated the parameter, we kind of lost some information. Notice that in the second set of equations, x and y can never be negative, can they? Because t squared is always positive or zero. So that second set of parametric equations is not the entire line. It's really half the line. It's the starting at zero and going off like that. It's not the full line, is it? It doesn't have any of the negative portion of that line. It's the line in the first quadrant only. So they aren't quite the same. Kind of neat, isn't it? Okay, let me ask you another question. Here's another set of parametric equations. What do they look like? What's the graph going to be? And the equations are pretty simple. X equals sine t, y equals cosine t. What's that going to be if I graph it in parametric mode? Well, we can eliminate the parameter, can't we? Just like we did before. Remember our fundamental identity, x squared plus y squared equals 1. So we have sine squared plus cosine squared equals 1. Wow. We have now a circle of radius 1 and center 0, 0. What's the orientation of this circle, though? Here's a picture of it, but what's its orientation? We've lost the orientation when we eliminated the parameter, but we can check it by going back to the original equations. When t is 0, where are we on that circle? Well, when t is 0, x is 0 and y is 1. So we're at the point when x is 0 and y is 1, we're up at the top. But how about when t is pi over 2? Well, now x is sine of pi over 2 or 1 and y is 0. So we're over there on the x-axis, on the positive x-axis, aren't we? The orientation here is clockwise. In that previous problem we did earlier in this lecture, the orientation was counterclockwise. We've kind of flipped the orientation by flipping the roles of sine and cosine. Kind of curious, isn't it? All right. I hope you enjoyed this lecture on parametric equations. Next lecture, we'll see even prettier pictures. We'll talk about what are called polar coordinates. This will seem familiar to you when you remember how we described a point in the plane using the angle it makes with the horizontal, the angle it makes with the horizontal and its distance to the origin. So it'll be kind of a generalization of that idea. We'll describe points using a coordinate system based on the distance to the origin and the angle it makes with the positive x-axis. And again, we'll see some really pretty graphs as we go along. So see you next time when we talk about polar coordinates.